All right, problem 24 says, which of the following differential equations for a population P could model the logistic growth shown in the figure above? So I know we didn't do a lot of studying this year on logistics growth, but you do have the basics that you need to figure out the answer here. Because really all you need to know about a logistics growth function is that they have this shape where they have like an upper capacity, so they have a horizontal asymptote up above, and then they also have a horizontal asymptote down below at 0, okay? And then they also have this symmetry sort of like in the middle, like between these horizontal asymptotes, the middle would be a point of inflection. So this would have, so in this case, this problem, you can tell that the derivative basically when p equals 0, so that's down here, would be 0. You can tell the derivative of this function with respect to time when p is 200 is 0 because of this asymptote at the top. And then every once in a while you might find it helpful to know that your graph changed concavity, like at the middle point there where p is 100. So that would be, so the second derivative when p is 100 would be 0. So hopefully that makes sense. So anyway, so those are kind of the basics. You just kind of know the shape, and then you know these little facts about the asymptotes and the point of inflection. And then I'm going to use the asymptotes to pick out the answer. I'll be able to rule A in, and then it would be easy to similarly rule the rest out. Okay, so I'm just going to show how to rule A in, and then could leave it up to you to rule the rest out. And then feel free if you want to play around with this fact also to see if you could maybe just lean on this one to rule things in or out. So anyway, so I'm just going to lean on the fact that these asymptotes, the derivative at the p-value of 200 and 0 would have to be 0, especially since these are all derivative functions. So if you look at option A, if you were to set the derivative equal to 0 and then solve for p, basically I'm going to show that you would get p equals 0 and p equals 200. Whereas if you did the same thing for the rest, you wouldn't get those values. So let's just put 0 in for the derivative. And then I personally like to turn these decimals into fractions. Everybody has their style. By the time you're in calculus, you get to have your own thing that you like. So if you like the decimals better, go for it. And then my style is to multiply both sides by 1,000 and clear the fractions out. So I'd get 0 still on the left side, and then I'd get 200p minus p squared. And then remember, we're solving for the p values that give your derivative a derivative of 0. So you could factor p out. And then hopefully you can see here that you'd get p equals 0. That's this one. That's this one. And then you'd get p equals 200. And that's this one. So there you go. So that's how I'd rule A in. And then you could go through the exact same steps. So start ruling B through E out. By the time you rule 1 or 2 out, you realize that you've got it. So you wouldn't have to do all of them once you kind of get the gist of it. Hopefully that makes sense. Okay, for problem 25, it says let f be the function defined above where c and d are constants. If f is differentiable at x equals 2, what is the value of c plus d? And whatever you do, don't do what I tend to do, which is do everything right and then forget to add c and d together and circle the wrong thing. Anyway, don't do that. Okay, so let's look at this. So if this function is differentiable, so you have this piecewise defined function, right? It's kind of a line graph and then it's a parabola. So just a quick generalization, if you have a line graph and then a parabola, if your line graph ends at 2 and then your parabola picks up at 2, if they're not connected, then you're not going to have something that's differentiable. So your graph has to be connected. And so that means that that means that the line graph and the parabola have to hook up, which means at 2, they would have to have the same y coordinate. So that's going to be one piece where you plug 2 into this function, which would give you, plug it in for x, you'd get 2c plus d. And then you plug 2 into this function for x, you get 4 minus 2c. And then this is us saying, like, your graph has to be continuous at 2. And so the thing is that even though I can simplify this a bit, like I'd add the 2c over, I'd get maybe this. I still have 2 unknowns. But that's okay, because just because the 2 graphs connect doesn't mean that they don't create like a corner or like a cusp situation, in which case your derivative would be different coming at it from the left and right side. And so you need your double-sided derivative to be the same. So you basically need not only for them to connect at 2, but at 2 you also need the slope of the tangent line coming in from the left side to equal the slope of the tangent line coming in from the right side for you to have that smooth kind of transition there and for your graph to be truly differentiable. So you're avoiding corners and cusps by taking the derivative of the top. And so the derivative with respect to x of cx plus d would just be c. And then the derivative of the second piece with respect to x would be 2x minus c. And when x is 2, you need these two things to equal each other. Hopefully that makes sense. And then you just solve for c. So boom, boom, boom. Looks like we're getting c would have to be 2. And if c is 2, you could take that and plug it back into this function where we're at least making your graph, make sure your graph is continuous. Plug the 2 in, you'd have 8 plus d is 4, so d would have to be negative 4. And then, like I said before, don't forget to add them together. So c plus d would be negative 2. Oh, it's always such a relief when I actually get the answer I'm supposed to get. Anyway, hopefully that makes sense. So this equation right here was basically us making sure the graph is continuous at x equals 2. So that transitional number here. And then this right here was us making sure that the derivatives, let's see, how do I want to say this? The left-sided and right-sided derivatives equal each other. At that transitional number of 2. There we go. All right, hopefully that makes sense, you guys.